Hello, my name is Andy Schweitzer. This is a little video on how to use a mass-to-mass calculation. From this particular video, we'll be showing an actual problem from start to finish. You should note that from mass, you really can't do any calculation except converting to moles. We'll use the molar mass in order to flip back and forth. This is the relationship between mass and moles. In moles, you can do your stoic calculations. You also, if you were an actual number of particles, you could do this as well. We'll use Avogadro's number to do this. Now, with that said, I'm assuming from the last video or from class that you can flip back and forth between mass and moles. So I'm going to go through and do a simple problem. H2 plus O2 yields H2O. I need 2 oxygens here, 4 hydrogens, so 2 there. Keep in mind that the coefficients are simply the rate used. 2 hydrogens, 1 oxygen, and produces 2 waters. Molar mass of this guy is 2 grams per mole, and this guy is 32 grams per mole, and this guy is 18 grams per mole. I like to put them above the top in parentheses. It's a tool that I can use later on. Again, the molar mass is the mass of this number of particles, MOL, moles. 18 grams per mole. You might say, okay, if you have 18 grams per mole, how much actual mass do you have? None. It's just a relationship. If you're making $50 per hour, how much money did you make? How long did you work? That's the same type of relationship. So in this case, let's say we have, let's go with 10 grams of each. As tempting as it is, okay, to say equal masses, use it twice as fast, this is my limiting reactant, cannot do that. Absolutely cannot do any stoic calculation with mass. As you get better and better, and in your head you can do a linear relationship between the mass and moles, that's maybe fine. But right now, everything gets converted to moles. So I'm going to set up an ICE table, ISE, and this has to be in moles. My initial amount in moles. Alright, so 10 grams, let's do the hydrogen first. Dot line, grams to moles, 1 mole is 2 grams, so I have 5 moles. 5 moles of this guy. And 10 grams, dot line, get rid of grams, go to moles. 1 mole is 32 grams. And this is going to be about a third. 10 divided by 32 for an exact value, 0.31 moles. 0.31 moles. Now, from this point, I can make an assessment as to which one I think is going to be the limiting reactant. I'm going to say I think it's the oxygen. Therefore, I will go minus 0.31 down to 0, and I'll show my stoic ratio. I'll jump from here to here to figure out how much I need of this guy. 0.31 outline at a 1 to 2 ratio is 0.62 moles. Again, I'm solving for a reactant, so that is a need, and the reactant is H2. 0.62 moles is what I need. Subtract from that is going to be 4.4 approximately. Okay. Maybe 4.38 to be exact, and I will put that in there exact. Alright, there we go. Now, none of this is left. This is essentially means this has gone to completion, meaning that we have swung all the way to products until one of our reactants has run out. I didn't have any of this to begin with, and you should note that this will 0 moles to begin with, and then I will gain 0.62 moles, 1:2 ratio. You'd want to show your work here. Also equals 0.62 moles of H2O. And at this point, I would simply answer the questions that they want me to answer. If the question asks me to just simply give me the moles of water produced, okay, this is my answer. If they want to know the mass, or I should say the moles of hydrogen left over, this is the moles of hydrogen left over. But if they want me to figure out the, in this case, the mass, well, I need to use the mole mass to flip back. Or if they want me to know the number of particles, I use the Avogadro's number to flip that back. So let's say they want to say how much mass of hydrogen is, let's go mass of product, okay? So mass of water produced. All right. So it's going to be 0.62 moles, dot line, get rid of moles, and go to grams. Again, I'm using molar mass. The molar mass is 18 grams per mole. And I would go 1 mole, 18 grams, so now I'm multiplying rather than dividing. 0.62 times 18 equals 11.16 grams. Equals 11.16 grams. It's always important to ask yourself, does this number make sense? I had 20 grams of overall material here, and I'm only getting 11 grams of product. Sometimes this throws kids for a loop. Why am I not having conservation of mass? I'm just simply rearranging particles. I should not gain or lose any particles, and therefore I shouldn't gain or lose any mass. All of my oxygen got used up, so that means 10 grams got kicked over to product. These oxygens are going to weigh 10 grams. But not all my hydrogen got used. So it would appear that only about 1.16 grams of the hydrogen got moved over. The rest of it went unreacted. So that is why I don't have a full 20 grams here, because some of the hydrogen went unreacted. You could even verify that. How much does 4.38 grams of hydrogen weigh? I'm going to estimate, based on the fact that 1.16 grams moved over, we're talking 8.84 grams. Let's do the math here. If I have 4.38 moles at 1 mole, 2 grams, and pretty easy to see, 4.38 times 2 is 8.76 grams. Oof. 8.76 grams of H2 that is in excess. Very common question that you'd want to ask or answer. If we wanted to go to number of particles, I would simply use the Avogadro's number to do that. I'll get to show just one example of that. 4.38 moles, dot line, get rid of moles and go to actual atoms, or let's go molecules of H2. 1 mole, 6.022 e to the 23rd. 4.38 times 6.022 e to the 23rd gives me 2.63 to the 24th. 2.63 e to the 24th molecules. All right. Only thing I would add on here, again, this is an example of going from mass to moles. Do your stoichiometry in moles and then back to mass. That's pretty common calculation. One place you can actually go to for moles that isn't on here would be to liters of gas, and make sure you're dealing with a gas. Let's take a moment, and I'm at a page here. Let's look at liters of gas. Is there a relationship between liters and moles? Well, gases, they are a little different bug. If we have a balloon with some particles flying around inside of it, you should note that only reason why that balloon is inflated is because, well, particles in flight are smashing into the walls, providing pressure, which can counterbalance the pressure on the outside. So there are a lot of factors that might affect the volume of this balloon versus the number of particles inside. So we have some conditions that need to be met, just to say we're all on an even playing field. And that would be the temperature, okay, and the pressure. These are two variables that can vary controlling the size of the balloon. So if we say our temperature is going to be 0 degrees Celsius or 273 Kelvin, and our pressure is 1 atmosphere, given those conditions, right, with that sort of environment set up, 1 mole of any gas, it doesn't matter, unlike mass, which everything has different masses, particles not the same. 1 mole of any gas equals 22.4 liters. This is for any gas. Now, in my previous problem, if I were to list out, okay, this is a gas, this is a gas, and this is a gas, okay? All right, so all of our mass to volume calculations, mass calculations have to be sort of moved to moles first. But really, only thing we cannot do these calculations in is mass. So if we're in moles, all right, I can easily say for this calculation, 2H2 plus O2 yields 2H2O, that if I have 2 liters of this, 2 liters of this, how many of this will I get? Well, in mass, I can't do this. But in volume, I can, because every particle acts the same. I have equal quantities. This is the limiting reactant. Therefore, this is my initial. My storage ratio will be to -2, -1, +2, and this will be in the end down to 0. This will be 1, and this will be 2 liters. Everything would have to be in liters. Everything would have to be gases. You could not have a liquid in here anywhere, or, well, at least, yeah, you couldn't have a liquid or a solid. Just gases. This only works with gases. You could flip these things, go 2 liters, dot line, get rid of liters, go to moles. 1 mole equals 22.4 liters. 2 divided by 22.4 gives you 0.089 moles. 0.089 moles. And then you could run this thing rather than with that number instead, 0.089 moles. And then you could just flip everything to moles and run it just like a mole to mole calculation. That is where we'll stop.